Hi everyone, welcome to the 14th occurrence of Nomadic Labs Research Seminar. Today's speaker is Peter Thiemann. So Peter Thiemann is a professor at University of Freiburg, where he leads the programming language group. The focus of his recent research is on gradual typing, advanced type systems for communication, and their application in the setting of blockchains. Today he is here with us to talk about oracles and contract modules. Thank you, Peter. I'll let you start your presentation.
Yeah, thank you very much, Remy. And as he said, so this is a talk about oracles and contract modules. And what I'm presenting is work I've done in collaboration with my postdoc, Ha, and with my master's student, Tamara. So here's a short overview, and we'll start with an overview, so I won't bore you with that. Right. Even though I might be preaching to the choir, all this happens in the context of blockchain, in particular of the Tezos blockchain. So what we're talking about, and I'm just repeating this so that you get into the mood. We're really talking about this kind of immutable list of digital records, which the blockchain people like to call a ledger because it reminds them of the financial tradition here. Other people just call it prosaically an append-only log. So the specialty of the blockchain is that this log is distributed and it's replicated over a whole peer-to-peer network, and where ideally everyone has the same rights and participates equally. And the idea is, of course, that this network is open, and also that pretty much all the information on this network is open. The way that things proceed and the way that this blockchain is managed is by consensus, which means that the people on the network, the nodes on the network, have to consent on what is the next stage of the chain. And if more than 50% of the nodes on the network are honest, then this happens to be unforgeable. And it turns out that blockchain was the first successful implementation method for cryptocurrency, which was Bitcoin, of course. Well, technically speaking, there's a bit more behind it. So we've got a self-verifying data structure here, which means the list structure is not just a list structure, but the links are made up by using hash pointers, so that essentially the root pointer incorporates all the information of the whole chain, at least the hash of the root pointer does. So then also in the traditional setting, list items are really blocks of transaction data, which tell you how the cryptocurrency is moved around between the different identities that are present on the chain. So the more interesting application to me, and I guess to most of our listeners, is smart contracts. Some people like to say that smart contracts are neither smart nor contracts, but in fact, they are just programs and data which is stored on the blockchain. And that's actually the scope most of the time of these programs. So they operate on the ledger, which means that inherently they also manipulate the some amount of the cryptocurrency. As we will see, the cryptocurrency, the presence of a cryptocurrency is also somehow a requirement that the blockchain can survive. And then, after consensus, really everything on the blockchain is deterministic. So the program execution on the blockchain is entirely deterministic. It's determined by the transactions that start, and it's determined by the state of the previous blocks, so of the whole history in some sense. So what's also interesting about blockchain is that we have that we have a replicated computation mechanism, some kind of a global computer, because all the calculations are validated many, many times throughout the peer-to-peer network. Now, depending on the technology, obviously. So this is very nice because it's a fail-safe means of doing computation, and it's unforgeable. It's also unforgiving, and so this has been popularized by this activist and attorney Lawrence Lessig, who came up with this phrase "code is law," and also in the sense of Nick Szabo, it's dry code, which really means that things are executed, contracts are executed literally, and even if you don't trust your contract opponents, the other persons and entities in your contract, still the contract is going to be executed. And Nick compared it to wet code, which is code which are contracts executed by people who make amendments, take shortcuts, and all that. Yeah, code doesn't do that, and that's what makes contracts on the blockchain interesting in this financial area. But then, I already mentioned there is a cryptocurrency involved. There are a couple of places where cost is involved. So programs and data stored on the blockchain, there's a cost for storing. There's also a cost for each execution step. Okay. Well, and that gets us to our topic, namely things a contract cannot do, or maybe should not do. So the first that I list here are things the contract cannot do, and then the last two are things that the contract shouldn't do. So firstly, randomness. Now, suppose you want to write some sort of contract that does a lottery and that needs some random input in order to make a choice. This is pretty hard to do on the blockchain. Because, well, everything is open. Even if you have some sort of pseudo-random generator, it's going to be predictable. So if you want to create some sort of tie-breaking mechanism or something like that, that is quite hard. This is something that a contract is not really well equipped to do. Another thing, external triggers, things that happen in the outside world. I'm going to present you some examples in the next few slides here. Well, the blockchain is a closed system. So the only thing that happens are transactions that come in, and usually they just tell you, start this contract or do this kind of transfer. So you can't react. Normally, you can't react to things that happen in the real world. Then there's also timers. So you can't say, start this contract not now, but do it in 15 minutes or 15 years, maybe. Another thing things you shouldn't do, let's move to that. For example, computation-intensive algorithms that operate on large data, that's not really a good idea because the algorithm is just going to cost you way too much, and also storing the data is going to cost you too much. So you need to find more cost-effective ways of doing that. Last point, if you have proprietary algorithms, it's also not a good idea to store them on the blockchain. Well, because it's an open system now, so your nice IP will be gone quickly once it's stored in the open. So it would be better not to run them on the blockchain. Well, these problems are kind of general, and they're not restricted to any particular blockchain technology. And the answer of the blockchain people is oracles. So just in order not to have to come up with my own definition here, there is a paper which is called The Study of Blockchain Oracles. I'm not going to make some sort of advertising for the paper, just let me steal the definition. So blockchain oracles are third-party services that provide smart contracts with external information. So oracles serve as bridges between the blockchain and the outside world. And then it goes on to do some sort of categorization, finding some typology of oracles. So they could be software oracles that kind of process online sources, could be hardware oracles measure the temperature in your local pool. Humans, like who won the car race or who won the bike race. So this is information that at some point will have to be entered by humans. Or they could be computation-based. They could be single source, or they could be consensus-based. So there are various ways that an oracle could work. But in all cases, there is some trust involved. So everything that's not running directly on the blockchain requires trust. And I guess the best way to trust is to take things in your own hand. So if there are the means to do these things by yourself through your own programs, well, you trust your own programs. So that's what your system might want to, oh, this is interesting, might want to rely on foremost. Okay, so now it seems like I am hanging here. That's the worst case scenario. Something is still working. I have no idea if you can still hear me.
Do you hear me, Peter?
I can hear you, but I think something is seriously hanging.
We can hear you well, and we can still see your screen, but we see you switching page.
I think it was just hanging, so now it works again. I have no idea what was going on.
Okay, fine.
Okay, sorry about that technical intermission. Right, so here are some example uses for oracles. So this is actually a classic one. Yeah, so automatically claim a file claim if a flight is delayed. Now, obviously, somehow the flight information needs to get on the blockchain, or pay out the bets when race results are in. And somehow I'm associating this to horse races, but I mean, it could be any kind of race. Yeah, and in both cases, I would claim that this is some information that some people need to somehow type into a computer. Then it maybe gets turned into a URL, and then somehow the oracle can pick it up. So the next one here is sell my bitcoins if the exchange rate reaches a certain threshold. Well, that can be quite automated these days, and you just need to connect to some Bitcoin exchange. And the last one is a time trigger. So if you have a lottery or an auction, you want to finish that after 48 hours. Okay, so you also need to trust some sort of oracle to send the closing message after the time has elapsed. But you could also use the same technology, as I'll show you, to just automatize processes. So maybe you just want to run a transaction when the fees are low, or you want to optimize things. Maybe you want the best price or the best throughput, and you're willing to pay a certain amount for the best throughput. Or you could just, as the user of the auction, want to program a bot that does the auction for you. Or maybe you just want to create some NFT kind of token. All right. So what are we proposing? Well, so tools for that are part of the project that I'm working on, which is the Coke project, which is really about orchestrating contracts on the Tezos blockchain. So it works on Tezos, and currently, what I'm want to talk about today is how to write oracles and to make processes automatic using OCaml programs that interact directly with the Tezos blockchain. And our medicine here is a type-safe API that allows you to do that, or that you can also do it in a fully integrated way using something that we call contract modules. And in what follows, I'll just give you some short insights into this. So I think my video is mostly broken, but that's probably not the most important here. Right, let's have a look at the contract API. So, of course, out of the box, Tezos has facilities so that you can programmatically access it. So actually, there are two ways. So if you want to use Tezos, obviously you have to run the Tezos node, and the Tezos node has a command line interface which you can use, and then you can do all these things using shell programs. So that's one thing. Or you can also, there's also an RPC API which you can use directly with, any language that allows you to connect to some RPC API. And here I'm just giving two examples. The API is vast and it provides many more technical entry points. So here's just one where you have to identify a contract, and then you can ask for the entry points, for the type of an entry point of a contract. There's also another call where you can just list the entry points in case you don't know them. And of course, the type is important because if you want to interact with the contract in a typed way, well, you need to have a means of checking that the type of your input is right. Now, similarly here, there's also another RPC call that allows you to obtain the storage of a contract. Obviously, that's also going to be important if you want to, let's say you have this contract that runs an auction, and you want to have a look at your current bid or at the current highest bid, then obviously you might want to look into the storage. So then you can also use, the code that comes with the client also provides a library, and the library also provides a thin wrapper that you can also use programmatically directly in order to access these functionalities. The drawback is, well, the APIs are pretty large. They are designed to provide the maximum functionality, so there's not much abstraction really going on, and the entire interface is string-based. So the way that you exchange information with the contract is really on a string level, yeah. Okay, so let me show you an example contract, and then we're going to look at that example contract, well, essentially that contract, with the two approaches that I want to put forward. So just as a reminder, a Michelson program can be viewed as a function that takes a parameter and its current storage, and then returns an operation list, and then the updated storage. Right, so the way that you define it is like this. So this defines a Michelson contract with two entry points. One is called closed, the second is called bid, and the name of the game, the objective of the contract is to provide some sort of very primitive auction. And for the bid entry point, the idea is that the actual amount that we want to bid is in the transferred amount. And then the storage is also very simple. It has a flag whether bidding is enabled, and then it has another pair. One is the address of the contract owner, because, well, if you close the auction, you should better be the owner. And then there's another address which indicates the current highest bidder. So, and to make things really, really simple, the contract is active as soon as it is deployed, and the current highest bid is the balance of the contract. Now, so I'm discounting all fees, etc., that are around. So just to keep things simple. Yeah. So what's the purpose of bid? Well, if you bid and the amount that you send is not higher than the current highest bid, then the contract will just fail, and it will cost you nothing. Otherwise, you return the previous highest bid and update. Okay, and this means that you're going to return it to the previous highest bidder, so that they get their money back. So that will appear in the operation list as a subsidiary transaction. Close means the obvious thing. If you're the owner, if you're not the owner, then close will just fail. Otherwise, close the auction and transfer the contract's balance to the owner. And this is also something what's not in the contract. Obviously, there is some side condition that, well, if you have cashed in the contract balance, then you actually deliver the goods that have been up for auction. Right. So how would we access that? So this is code for the API for the development version that we're currently in the process of releasing. So firstly, you would have to obtain a typed handle for the contract. So here, that's this. So CL, by the way, stands for the module that contains all the contract code. So, I mean, just imagine it says it's short for contract library. Create typed handle takes the source of the auction script, and then it takes the type of the parameter, well, a type representation of the type of the parameter and the representation of the type of the storage, and then it creates a typed handle. So, and the typed handle has internalized both of these types. So firstly here, this is the internalization of the type of the two entry points. So, well, which are joined as one entry point with a sum type as an input. And then here, this type of the storage is also translated into a suitable OCaml type. And that's basically the idea. So as we know, the Michelson types are very close to OCaml types. So there is a translation that goes at least in the OCaml direction and not necessarily in the reverse direction. And this is used in this case. And here the usual magic is applied. So this type representation is defined by a GIDT. Then the type of this type representation has a parameter that's exactly this unit either type. And I mean, this is kind of standard things. Okay, so sorry, I'm skipping over to many things at once. Now, let's automatize this contract. So firstly, let us assume the author would like to close the contract 48 hours after the auction was created. Okay, what would you have to do? Well, firstly, you would have to tell the contract library under which authority you want to issue your further commands. And this is very similar to what you would do on the command line interface. So local, you can define aliases, and essentially, and your local node can administer several aliases. So first you have to say, okay, this is me, right? And then you create the initial store, which has the type that we just saw. So I register myself as the owner and also as the first bidder. And then I do the origination of the contract. That's the Tezos way of deploying a contract on the blockchain. And I can do that using the typed handle. And since I have this typed handle, so that's connected to the type of the initial store. So I know that I won't have any sort of typing error when I do this origination. Yeah, and I'm actually depositing one Tezi with this contract. Okay, and once this is done, well, then I can sleep for 48 hours, and then I'm calling the closing contract again. So that's the close entry point, and there you go. Now, so that's something that you might want to do as the author. If you're at the other end, you might want to implement some sort of bidding strategy. In this case, you would have to obtain the contract differently, because now somebody else has published this hash and you have to connect to that contract. So in that case, so you start out with the hash. So in this variable, this contains the hash, and then you create the contract really from hash. So that's another entry point to our library. And there you have to give the same types again. Of course, I don't think I said that before. Of course, when you do one of those functions to inject the contract into the typed handle, of course, at that point, all the type information is checked. And there are standard entry points for that in the Tezos code. And we are using, there are even RPCs to do that. And that's what we're using. And then you can actually do some sort of polling strategy that goes like every 5 minutes and checks for the bidding. So let's just see what goes on. So here, the auction handle also knows about the type of the parameters, and it knows about the type of the storage. So there is a get storage operation, which returns you a typed version of the storage. So it has exactly the format that we saw before. Then we can obtain, then we can also obtain the balance. That's yet another RPC call under the hood. And then we can do some logic in order to find out what goes on. So here there's something interesting going on. Here we are now calling the contract through this auction handle, and we're using the right entry point, which is bidding. And we are so here we are calculating some bid amount, which is higher than the current highest bid, but still at most my own limit. And this can go wrong. So this can fail. And in principle, we could also analyze the reason why it fails. So this one doesn't, this code, to keep it on the page, it doesn't really check out what's going wrong. I mean, in the meantime, someone else could have placed a higher bid so that my bid is not the highest anymore. So that would be one reason of failing. But there could be other technical reasons for failing just as well. And here we're just doing not anything intelligent, but we're just retrying the whole loop here, obtaining the balance again, etc. Okay, right. So that was approach one. Right. So this is a little bit more here. If we dig deeper, then there are also some interesting technical things to actually get the code to look close to that. So, for example, there are observer functions like get the storage, get the balance. These observer functions, they succeed always. But if we call or originate the contract, we also need to put in a fee. And we didn't mention that in the previous one. So one thing that we can do in the library is to set up a certain fee strategy, and then this fee handling is done automatically. And that also can lead to whether or not the contract is accepted. Also, starting the contract may time out for various reasons. And you might want to cope with that as well. So at present, we are offering a low-level interface which does a type-safe handling, but is still explicit about fees and waiting and polling the states of the contract invocations. And it uses exceptions in order to communicate things that went wrong. In the next step, we are actually aiming at a higher level interface where you can have programmable strategies for handling fees and all that, and kind of prescribing ways to wiggle you out of failure situations. And then it's not going to be waiting and polling, but we're going to use standard concurrency abstractions, promises, futures, whatever you want to call them, instead of some explicit polling code. Okay, let's move on to the last part, which is contract modules. And so they are related to the API, but they incorporate even more of the statically available information and cook that into a full interface. So the objective is even better integration. So even less fixed API that you have to learn, but there is less flexibility. So the way things go are that you need to describe the contract by a suitable signature. So before you have some API calls that come with that accept type representations, which works, but you can argue that it's kind of bulky and not that nice, and it's also somehow dynamic. So here you describe a contract by a suitable signature, and you will see an example in 1 or 2 slides. Then from that, we are generating code, namely an interface and the implementation. And that code actually has a custom type and exception declarations and leads to the implementation, provides fully integrated and directly callable code. So instead of doing, I should have done the same example as in the previous one, which I didn't. This example would look even more elegant. To talk about this, I actually have to show you some Michelson code, but I guess if you're listening here, then you're familiar with these things. This is another option, so it just has close and bit. I should have used the same storage. I'm not sure why I didn't. And so here there's actually some code, and what I would like to show basically is, so this code kind of analyzes the arguments, and then at some point, if you're in this closing part and you're not the owner, so that's this comparison up here, then, so the storage is even actively wrong. Yes, yeah. Let me not read the code right now. Then we are failing with a message. Okay, you are not the owner. Okay. So in bidding, there are also a couple of ways that you couldn't fail. For example, if you don't bid enough, whatever enough is, then the contract will fail. And also, if the contract is already closed and you try to bid, it will fail. If your bid is too low, it will fail. And then here there's some random thing that also makes it fail. And all these are legal means to fail in a Michelson contract. Right. So, of course, you can type check this. Yeah, Tezos does it every day, every second, maybe even. You can translate these Michelson types to OCaml types. I showed you examples, not the scheme. The hard part is characterizing the failures. And also checking coverage of the failures. And this leads to, on top of typing, we also need to analyze the occurrences of the fail-with instructions of Michelson. And we need to analyze the values that are on top of the stack when the fail-with occurs, because that's what's actually reported, and that's the visible interaction with the outside world that we could analyze and turn into an exception. So what we want to say now in a contract module is something like this. So we define a contract type. Well, the syntax is obviously mostly stolen from OCaml. So we want a contract type, my contract. So the signature is, okay, we define a couple of entry points. So we have a paid entry point, which means that I'm reckoning this entry point is accompanied with a non-zero amount. And the name of the entry point, and then the parameters. And here at this point, I can write an OCaml type, but it's only valid if it also has a counterpart in Michelson. So now the second part of the description, raises here, is somehow similar to throws. To exception declarations in Java. So this defines all the ways that the contract can fail and gives it, so to speak, a name. So raises closed means there is a fail with that gives the message closed. This one says there's a fail with that gives the message bit too low. But I don't really want to report that in OCaml as a string. instead I want to use this identifier as an exception to low in OCaml. Right, so if the answer is 42, then I would like to report that as the answer, because it's the answer to life, the universe, and everything. So it should be reported properly. If it's just an int, well, then I would like to report it as an exception failed with, but which takes this int as a parameter. Okay, so I think the second entry point doesn't have any new things. So it's the entry point. That's the name of the entry point. And right, so it just takes a unit. We don't care about the value here. And it just raises this not owner. It just fails with not owner. Right. Yeah, and that here we see the documentation and all that. Yeah. So and our compiler essentially checks that this contract module description fits with the code, so that all the exceptions that we're declaring here, that the Michelson code doesn't throw more exceptions than we are declaring here. All right. So this is then compiled, as I already mentioned, into an interface and the corresponding implementation. Each entry point is compiled to a function. The code is a function with just standard arguments, and with standard arguments, I mean technical arguments about fees and all that. And then there are arguments that correspond to the parameter type. Yeah, so standard arguments are the ones that you also have or may have in the contract library, in the Tezos contract library. Right. So if it's paid, then payment is required, which leads to an extra argument. Raises means that we specify potential values for fail with, and these get translated into exceptions. So the checking that goes on is type checking. Well, that's not surprising. On top of that, we have some symbolic interpretation, which analyzes the values that reach fail with, and also the uses of amount, because that should match the paid declarations that we have for the entry points. So a path and entry point is only allowed to use the amount instruction if it actually declares itself as paid. So here's an example of a generated signature. So the module type is obviously derived from the it's obviously derived from the contract module name. Then here we have an exception type, which reflects the exceptions that we have declared. Yeah, so if we don't say anything, then the exception string that we caught is just translated into an identifier here, and the other ones, they are taken over from the declarations in the contract module. Right, then bidding. Well, we need the hash for a contract. Then potentially we need to pass over a fee if the standard fee doesn't. If we don't want to use the standard fee, and we need to pass over an amount. This argument is present because of the paid declaration. Then here we have an integer for the argument here, and then we get the usual status and the bit errors as declared inside of the monad. So that's just in order not to have to deal with exceptions. And the other one is very similar. So this one doesn't declare paid, so the amount is going to be an optional parameter here. And apart from that, okay, it has no extra. So the parameter for this entry point is unit, so we just have a unit at that point. Yeah, it could be omitted, but we chose to make it kind of uniform. Right, and that leads me to the summary. So we have I've given you an introduction into this API that we designed and contract modules. The objective is to automatize processes on the Tezos blockchain and also to implement oracles. So we're aiming really for different levels of integration now, because depending on what kind of user you are and what kind of applications you want to run. So we have a low-level interface, which is pretty much ready to go. We're aiming for this higher-level interface, which is based on the on concurrency primitives, and then we also have the modules, which is still upcoming. It's not yet ready for release, but there is some sort of preview here. We also have some underlying theory. So with the API, we have designed some mixed execution model, which means there's a specification of that incorporates a bunch of threads that run OCaml code along with the blockchain, and we have formalized the interaction between the contracts and this external code, and we've proven type safety and formalized these typed handles and established some interesting system invariants. And with that, I would like to thank you. Sorry for the technical hiccups. I think it's mostly my fault. And thanks for listening. And I'm happy for your questions.
Okay, thank you, Peter. I'm gonna read the question out loud if it's fine with you.
Sure.
So there are a few questions by Jan. The first one is there a way to deal with the difference between the actual time a call is performed and the time it is included in the chain?
Yeah, so that's a very good point. In fact, current thinking, and I would welcome input on that. So our current thinking is that we would like we designed the calls more or less all as synchronously happening. Now, so you immediately get some feedback, you get a handle, and then you would have to do the polling yourself and finding out when the call is actually incorporated in the chain. So that's essentially the difference to the high-level version. So in the high-level version, you would just chain together the different calls with the concurrency primitives. I mean, with monad-like binds, for example, and then the waiting would happen as part of the monad, and you would just carry on with your monadic code, and then the system or the strategy that you programmed into the monad would take care of that. I hope that answers the question. But I mean, if you really need some sort of checkpoint where you say, okay, at this point I want to make sure that things are included. At that point, yeah, we don't have that yet, but it would be easy to do. You would have to use some sort of synchronization primitive that says, okay, at this point sync, and let's not proceed over this checkpoint once until everything is incorporated into the blockchain.
Okay, Jan says it answers this question. Thank you. The next question is from Jan too. It's about the slide 21. He's wondering why we have to introduce the variable name v into the environment.
Yeah, actually, I was wondering about that myself when I don't think it's necessary. Yeah, so you can't really refer to it. Yes, yeah, you're correct. Yeah, so it should just be the type.
And so his next question is, raises declarations are over approximations of possible errors, right?
Yes, yeah, of course. Yeah, I mean, that's what, so symbolic execution is a static analysis technique. So you can only get over approximations of that, of course.
I guess this next question is a follow-up. So since most contracts have no loops, would it be possible to specify under which condition failures can happen? How are the values that provoke failures are specified? And is it possible to exploit them to avoid performing a call that will fail?
Oh, these are very interesting questions. I mean, the underlying technology of the symbolic interpreter is, of course, that there is some SMT solver behind it. So I think all those questions are within range. So the values are presently not specified. Is it, I mean, if we were in a live interaction, I guess I would ask if you think it would be a good idea to make a specification of which values are provoking the fail with. Now, I don't see a technical reason that would speak against it. Yeah, so you would get some sort of path formula anyway. You get some path formula anyway inside of the symbolic interpreter. So extract the formula that describes the values, but we didn't think of specifying it. So if you think that's a good idea, we could certainly do that. Yeah, and in this way you could, sure, I mean, this way you could actually avoid performing the call. So if you can already derive that it will fail from the input, yeah, but usually this formula will also involve somehow the storage and what, yeah. Yeah, so that's kind of, yeah, it could fail in one point, in one instance, depending on the current store, it could fail now, but in 5 minutes the store has changed and you could invoke it again.
Okay. Jan is asking as well if you re-implemented your own Michelson interpreter or if you're using an existing one.
Actually, I was so the students are doing that, and if you have recommendations of where the students should start, I'd be happy to point them to existing interpreters. Yeah, I would like to avoid that as much as possible. If there's work that's available, we'll be happy to do that.
I think Jan can answer you in the chat for this. Okay. And also he answered your previous question about if it would be a good idea, and he said, given the cost of a call, if you have some way to prevent stupid ones, that would be great.
Mm-hmm. Yeah. So is it so? I mean, so would it be a good idea to have this kind of specification reified? Okay. So like you would, so in the contract type, you would specify this as a precondition, for example. Yeah, and then already in the OCaml side, you could check the precondition, and then you could fail already in the API before even getting in touch with the blockchain. Yeah, that's a good point. That's a really good point. Yeah, thank you.
Okay, I have a question myself, if there is not more still. It's about the more high-level features. Like right now, you are generating an OCaml type that is static for something that is a bit dynamic, and at execution time, you will try to map the generated type with the contract on the chain. Would this be possible to check statically that the contract you are going to use has the right types, and would this be interesting?
Yeah, I mean that's actually the point of the contract modules, right? So for the contract modules, you do all the checks beforehand, and for the API, the way it's designed is as an embedded DSL in OCaml, and for that reason, I mean that's mainly the reason that you have this type representation business, and yeah, so that you get your results more quickly without having to write to do some sort of code generation. Yeah, but in principle, I mean, once the contract is deployed, or even once you have the code for the contract, you can do all the type checking and all the analysis you want, and you could incorporate that, of course, into the code that you generate. So did I understand the question right?
Yeah, if it means you need the contract public key in your code to statically check that the contract on the blockchain is.
Yeah, that's right. So in fact, there are two ways that we want to deploy these contract modules. So one would be I have the code and I can do the analysis locally. The other one is that I just find the contract hash and I come up with this description. Well, I can query all this information from the Tezos blockchain. I can obtain the code. I can get all the typing information that I want. I mean, and I would need the code in order to do this exception, the fail with analysis. I could a model that we would also like to implement at some point, that you just have the hash, get everything from the chain, and verify the module against that.
Thank you. And okay, Jan, a contract can accept as function as input. How do you deal with that kind of values?
Okay. Yeah, to be honest, I haven't thought about that yet. So is there a way to enter that into the string interface? Can you put that in as a lambda?
Let Jan answer that one. And he asks, can we build a bidirectional communication channel on top of the API, maybe following the same techniques as bidirectional communication is built by web application on top of HTTP? And also he answers yes to your previous question that we can encode it in the
okay, yeah, in that way, in that case, yeah, so there are methods to reify functions unless they are, so as long as they are pure functions, and well, you can't handle anything else inside of Michelson, so you could do that, yes. Yeah, but I haven't thought about that. So is it happening often to have first-class functions as contract arguments?
It's a shame that Jan cannot answer it directly.
Oh, sorry. Yeah, it's a proxy thing. That's. So all this is on record, so right? So I can later on watch a recording of the discussion.
Yeah.
Okay.
Yeah, for sure. There are.
We would have to make notes now.
They are hosted on YouTube afterwards. And, yeah. And Jan answered yes to your question if it's a usual thing. And so thank you again. And the next section will be about Tezos shell written in Rust, and it will be Jerusalem. Thank you again, Peter, and see you.
Yeah, thanks for having me. Bye-bye.